All right, today's lesson is about exponential functions. We're going to talk about two main topics here, starting with the properties of exponents. This should be a review for you from previous math classes where you learned about these properties. But let's start with the most basic property, that anything to the 0 power is 1. So anytime you see something that's to the 0 power, that's going to go right to 1. The second property that we'll talk about is when we are multiplying two terms that have the same base. Notice that these bases match. Then we add those exponents together. We combine the base and add the exponents together. So take a look at this first example here where we have 3 squared times 3 to the 4th. Since both of these have an exponent of, a base of 3, we add those exponents together to get 3 to the 6th power. In this next one here, we have to make sure that we are only combining when the bases match each other, which means that we're going to take the x's and add those exponents together. So we have an exponent of 3 plus an exponent of 2, so we get x to the 5th. And then for y, we have an exponent of 4 plus an exponent of 5, which is going to give us y to the 9th. So just making sure that we keep those bases separate when the bases are different. Our next rule tells us that if we're dividing with the same base, then we subtract those exponents. And we always subtract the numerator we subtract the numerator minus the denominator. So here's an example where we have 5 to the 6th power divided by 5 to the 4th power. Since both of these have the same base, we subtract their exponents and we get 5 to the 2nd power. Just like we did in our last example, we have to make sure that we keep the bases, or we only combine when the bases are the same. So for our x's, notice that this x on the bottom here, we don't actually see an exponent, but we know that it has an exponent of 1. So we have x to the 4th minus, or x to the 4 minus 1, which is going to give us x to the 3rd. And then for y's, we have y to the 3rd over y to the 5th, which means I have 3 minus 5, and that's going to give me y to the negative 2. We're going to talk about those negative exponents in just a minute here. But always remember that you do the top minus the bottom. Okay, that's one common mistake, is to mix the order of those. The next rule here says that if we have an exponent that's being multiplied to another exponent, that's being raised to another exponent, it looks like multiplication, and that's exactly what we do with the exponents. We multiply them together. So in this example where I have 4 squared that is to the power of 3, I multiply the exponents together to give me 4 to the power of 6. Our next rule is kind of a distribution concept, but understand and make sure you make a really important note that you can only distribute exponents with multiplication or division. So if I have a plus b to the power of m, this is not the same as a to the power of m plus b to the power of m. Okay, so we have to make sure that we only apply this rule when there's multiplication or division. So in this example here, because x squared and y to the 4th are being multiplied together, I can go ahead and distribute the 3. And you'll notice that I also combined this with the previous rule we just talked about. And so this is, when I distribute the 3 to the x squared, I'm going to multiply the 2 times the 3 to give me x to the 6th. And when I distribute the 3 to the y to the 4th, I'm going to multiply the 4 and the 3 to give me y to the 12th. As I said before, this also applies to division, so I am allowed to distribute when there's division, just like I could with multiplication. So when I distribute the 2 to the x to the 3rd, I multiply those exponents together, which gives me x to the 6th. And then when I distribute the 2 to the denominator to y to the 5th, I multiply those exponents and I get y to the power of 10. Now the last rule here is the rule for negative exponents, and when we have a negative exponent, our goal is to write it as a positive exponent, and the way that we do that is by taking the reciprocal or moving the negative part to the other side of a fraction. So if I have a to the power of negative m, then I can write that as 1 over a to the power of positive m. So all I've done is I've taken my term and I've moved it to the other side of the fraction to make the exponent a positive. Same thing would be true if the negative is in the denominator. So if I have 1 over a to the power of negative m, I can move this term up to the top, and when I move it to the top of the fraction, it becomes a positive m. So let's look at this in the context of this this first problem here. 3 to the power of negative 2. In order to make that a positive exponent, I need to move that entire piece into the denominator. So I'm going to get 1 over 3 to the power of positive 2. And in this example here, I want to point out that if we have a negative exponent, the only thing we're moving is the negative exponent. So this x squared has a positive exponent, so it's going to stay right where it is. And the y to the negative 3 is going to move up to the top to become a y to the positive 3. So those are the properties of exponents. You do need to know how to do that successfully in order to answer some of the questions on your quiz. And let's move on to some of the differences between exponential and linear and what we're looking for in a table. So we've talked about linear functions already, and we have a pretty good foundation here. But when I'm looking at a table of linear functions, I will notice that for a linear function, it's always adding the same number to get from one point to the next. Okay, so it's a constant change by addition, or it could be a constant change by subtraction. So in this table here, you'll see that we're subtracting 3 to get from each term. So linear functions have that constant change by addition or subtraction. Exponential functions, if you look at this table, what do we notice happening between each of these numbers? So to get from 3 to 6, I could look for addition, but I'll see very quickly that it's not adding the same thing every time. So you'll notice here that these tables are being multiplied by the same number every time, and that's what makes an exponential function. Now in this table, this doesn't look like multiplication right off the bat. We should recognize that this as division. I divide by 5 every time. Whoops, except I messed that up in this table. That should be a 1, and that should be a 1/5. So I divide by 5 every time, but it is important to know that dividing by 5 is the same thing as multiplying by 1/5. So this is still multiplication, it's just the multiplication of a fraction. And that's what we look for in a table for exponential functions. Let's talk very quickly about the graphs of exponential functions. This is the majority of your quiz, so this is where you really need to focus your energies and make sure you have a good understanding. So first of all, let's talk about the form of these exponential functions. They come in the form of a to the power of x. So you'll notice that the variable is in the exponent. That's what makes this an exponential function, as opposed to a power function where the variable is in the base. So power functions would be x to the power of n, some number, right? And your variable is in the base. So exponential functions, the variable is in the, the variable is in the exponent. Okay, we have exponential growth as long as the base of your function is greater than 1. So the base of the function must be greater than 1 for us to have exponential growth. Growth is exactly what it sounds like. It means that your graph grows from left to right. It's going to go up exponentially. Okay, exponential growth functions have a horizontal asymptote at y equals 0. You'll see that this line kind of flattens out. And the farther you look to the left, it will get closer and closer and closer to 0, but it won't actually ever touch it. So what this does is this impacts the range of your graph. It means that this graph only goes from 0 to infinity. And you'll notice that there's an open bracket on 0, a parenthesis, and that's because it will never actually reach 0. The domain, of course, is all real numbers. You can plug anything into an exponential function and get an answer out of it. So there's no trouble points with the domain at all. So that's a nice thing about exponential functions. We don't have to think too much about domain. The other kind of exponential function that we have is exponential decay, and all the same stuff applies. You'll notice that the graph looks a little different, and this happens when a is less than 1, but not negative. So really it's between 0 and 1. Okay, it's some fraction or decimal that's less than 1, and this is when it's declining or decaying from left to right. So as we look at the graph, you'll just see it looks like the reverse of exponential growth. But all the same things apply. It has a horizontal asymptote at y equals 0. The domain is still all real numbers. You can plug anything in here, but the range is from 0 to infinity. So it has that horizontal asymptote that stops it. The horizontal asymptote does apply to the range. So those are connected. So whatever your horizontal asymptote is, that's where your range is going to start. Okay, so that's important to know about the graphs of exponential functions. Just like any of the other functions that we've talked about, there are transformations that get applied. Specifically in this lesson, they focus only on translations. So if you are adding something or subtracting something to the outside of the function, that's the plus k at the end, it looks exactly like what you see. If it's plus k, then it's going to move up that many units. If it's minus k, then it's going to move down that many units. When it moves up, your horizontal asymptote and range will also change. So horizontal asymptote and range are going to change with that k value. Okay, so that's important to know. We'll talk a little bit more about that in just a minute. And then the h value on the inside here, that moves your graph left to right, and just like we've always talked about, this one is the opposite of what you see. So if it's x minus 2, if you've got a negative h in there, then it's going to move to the right, and if it's x plus a number, if it's a positive number in there, it's going to move it to the left. Okay, so these are the translations. So let's take a look at a couple of examples where you are going to identify what the function is. So we're trying to figure out, first of all, is that a value going to be greater than 1 or less than 1? So looking at this, this graph here, is our a value greater than 1 or less than 1? Since this is growing from left to right, the a value should be greater than 1. We don't know what it is. You don't have to identify what it is. You just need to know that it's greater than 1. And then we want to see what kind of translation has been applied. So the normal function, if you noticed on the graph, it starts at 1. I'm sorry, it has it crosses the y-axis at 1. But we should really be looking for that horizontal asymptote. That is the indicator of the translation that's happened. So since we have a horizontal asymptote at 2, that means that our function here has been moved up 2. And while we don't know the a value specifically, we do know that the a value has to be greater than 1. Okay, so let's take a look at this one here. This one, we can see that it hasn't been moved up at all, and we can see that because the horizontal asymptote is still at y equals 0. Oh, I want to go back real quick. I'm sorry. Because we've moved this up 2, this also means that the range of this function is now from 2 to infinity instead of 0 to infinity, because we've moved our graph up 2 units. So I said when there's a horizontal asymptote, that's going to apply to the range. That's what we're looking for exponential functions. Okay, this one here has not moved up or down at all. But we can see that it has been moved over this way, because typically this graph will cross the y-axis at 1, and this time it doesn't do that. Now, first question would be, is our a value greater than or less than 1? Because this one goes down from left to right, this is decay, so this means that a is less than 1. And we don't know what it is, but we don't need to. We just know it's less than 1. And we know that it's been moved over. So we can take a look at how many units it's been moved over, which in this case it's been moved over 3 units. Remember, to the right it's going to look like the opposite of what we see. So x minus 3 is what's going to go into this function here.